Hi folks, welcome back to educator.com. I'm Dan Fullerton and today we're going to talk about circuit analysis. Our goals are going to be to draw and interpret schematic diagrams of circuits, to solve both series and parallel circuit problems using VERP tables, to calculate equivalent resistances for resistors in both series and parallel configurations, and finally to calculate power and energy used in electric circuits. So let's start by talking about series circuits. Series circuits have only a single current path. If you remove any circuit, we must have a 3 ohm resistor and a 6 ohm resistor. 3 ohms, 6 ohms. And there has to be more to the circuit, but we'll just draw that piece for now. If the current through the 3 ohm resistor is 4 amps, so we have 4 amps going through the 3 ohm resistor, what's the potential difference across the 6 ohm resistor? Well, to answer this, I have to figure out the current going through the 6 ohm resistor. And if I have 4 amps going through the 3 ohm resistor, Kirchhoff's current law says I must have that same current here and same current here. What goes in must come out. So I must have 4 amps going through the 6 ohm resistor. Current does not get used up in a circuit. Well, now that I know the resistance and the current flow, I can find the voltage drop. The potential difference from one side to the other is going to be I times R, which is 4 amps times 6 ohms, or 24 volts. So if the current's going this way, we must drop 24 volts from the positive to the negative side as the current goes in that direction. What's the potential difference across the 6 ohm resistor? 24 volts. Let's take another look here. The diagram below represents currents in a segment of an electric circuit. What is the reading of ammeter A? So we've got an ammeter here, and here we have a junction where all of these come together. This is going to be a great place for us to apply Kirchhoff's current law, or the junction rule. The current coming into that junction must equal the current leaving that junction. So coming in, we have 2 amps, we have 3 amps. So in, we have 2 plus 3. And let's just assume for now that we'll call that current coming in, so plus A. And if we get a negative, we know it's going the opposite direction, must equal the current leaving. And the current leaving, well, here we've got our 4 amps, we've got 1 amp, and we've got 2 amps. So when I put this all together, 5 plus A equals 7. Therefore, A must equal 2 amps. And yes, it is going in. So our ammeter would read 2 amps. As we talk about basic series circuit analysis, we can use Kirchhoff's current law and Kirchhoff's voltage law along with Ohm's law to find a bunch of unknowns. But one of the most helpful tools, especially when you're starting out with simple circuits, is what I call a VERP table. I could use power equals I squared R, or I could use power equals V squared over R, since I know all of those things. We'll take the easy one right now. Power equals V times I. That'll be 0.008 watts dissipated in R1, or 8 milliwatts. The same for R2. The same for R3. And the total power dissipated is just going to be the sum of those, or I could find it by multiplying V times I down here. Either way, 0.008 plus 0.008 plus 0.008, or 12 times 0.002. Regardless, I'm going to get the same answer, 0.024. I'm dissipating 0.024 watts in my entire circuit. So that's basically how we're going to use these VERP tables to help us organize our information. Now, as I write these down, you'll notice that I'm skipping putting units anywhere. I'm assuming that V, potential difference, is in volts, current is in amps, R is in ohms, and power is in watts. So, let's take a look at another problem, current in a series circuit. A 2 ohm resistor and a 4 ohm resistor are connected in series with a 12 volt battery. Let's draw that first. We've got a 12 volt battery, and we have in there a 2 ohm resistor and a 4 ohm resistor. 2 ohms, 4 ohms. If the current through the 2 ohm resistor is 2 amperes, so we must have 2 amps flowing through the 2 ohm resistor, what's the current through the 4 ohm resistor? Oh, I don't even have to go make a verb table. This is just Kirchhoff's current law. I must have 2 amps flowing through there as well due to KCL. Kirchhoff's current law. I equals 2 amps. Very straightforward there. Let's talk about energy expenditure in a series circuit. In the circuit diagram below, we have 2 4-ohm resistors connected to a 16-volt battery as shown. Fill in a verb table for the circuit and determine the rate at which electrical energy is expended in the circuit. All right, let's call this R1 and this R2, so that when we do that now and make our verb table, we've got R1 R1, R2, and total. We don't need to add the ammeter in there because our ammeter should have a negligible effect on the circuit. All the ammeter does is provide us information. V, I, R, P. And we'll start by filling in what we know. R1 is 50 ohms. We know that we have a 120 volt source. We know the current over here, because the ammeter says it, is half an amp. That means we must have half an amp going through R1 and R2. So 0.5 amps, 0.5 amps. So we must have a total current of 0.5 amps. That must be the same. Now, let's start down here. We know 2 things in this row. If R equals V over I, 120 over 0.5, that's going to be 240. Our total resistance must be 240. Well, if our total resistance is 240 and R1 is 50 ohms, they're in series, so what do we add to 50 to get 240? Well, that must be 190 ohms. We can figure out the voltages now. V equals IR, half of 50 is going to be 25. Half of 190 is going to be 95. And of course, those potential drops will add up to our total potential drop. And if we want the power here too, one more step, V times I, half of 25 is 12.5 watts, half of 95 is 47.5 watts, and half of 120 is 60 watts, or add up 12.5 and 47.5. Now I know everything I need to about the circuit. I can go answer the questions. Calculate the equivalent resistance of the circuit. All right, that's easy. The equivalent resistance is our total resistance there, 240. The resistance of resistor R. Well, resistor R is R2. Its resistance is 190 ohms. We've answered that as well. And the power dissipated by the 50 ohm resistor. So the power dissipated by R1, 12.5 watts. By filling out our verb table, we've answered all these questions effectively. Let's take a look at a voltmeter in a series circuit. In the circuit represented in the diagram, what is the reading of voltmeter V? And it looks like we've got two resistors, and if this looks confusing at first, pretend the voltmeter's not there. If it's hooked up correctly, it shouldn't have any significant effect on your circuit. So as I take a look at this, let's call this R1, we'll call that R2, and we'll make our VERP table. R1, R2, total, V, I, R, P. All right, finishing our VERP table here. Let's go and let's fill in what we know already. R1 is 20 ohms, R2 is 10 ohms, our source is 60 volts. And as we look again, this is a series circuit again. Current is going through R1 and R2, and we can assume very little current through V, pretend it's not there, it has a negligible effect on the circuit. Therefore, we could find the total equivalent resistance. We just add them for a series circuit. 20 plus 10 is going to be 30. Once I have that, of course, I can figure out the current. I equals V over R, 60 over 30, that's going to be 2 amps. So if we have 2 amps going here, we must have 2 amps through R1 and R2. We can fill those in. And now it's pretty easy to go find the potential drop across R1. V equals IR by Ohm's law. 2 times 20 is 40. 2 times 10 is 20. And of course, those add up to our total. And while we're here, let's figure out the power. 40 times 2, power equals V times I. That'll be 80 watts. 20 times 2, 40 watts. And 60 times 2, 120. Or I could have added those up. So now to answer the question, what is the reading of voltmeter V? Voltmeter V is reading the potential drop across R1. So the potential drop across R1, just look up on my table, is 40 volts. Our answer must be 40 volts. All right, let's take a That's also 0.006. Now we must have 0.012 at this branch in the circuit, plus this 0.006 over here gives us 0.018. So all of the currents add together for the total. Now I could find R over here, V over I. 12 divided by 0.018 is going to give us 667. The same thing we'd have gotten if we calculated an equivalent resistance for the resistors in parallel using 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. Try it, it works out. Now, for the powers, well, that's just going to be V times I, or 0.072 watts. Same math for all three of these. And the total, we could add these three up, or 12 times 0.018 is going to give us 0.216 watts, or 216 milliwatts for the parallel circuit. Let's take a look here at another parallel circuit problem. We have a 15 ohm resistor, R1, and a 30 ohm resistor, R2, that are to be connected in parallel between points A and B in the circuit that contains a 90 volt battery. Complete the diagram to show the two resistors connected in parallel between A and B. So let's do that first. Well, if they're in parallel, we must have two current paths. So let's make that one of them, and we'll make that the other. Current has two different directions to go here, R1 and R2. Good. Now determine the potential difference across resistor R1 and calculate the current in resistor R2. Well, the potential difference across R1 has to be the same as the battery here. If this is a 90 volt difference between the two, and let's make this simple. Let's call the negative side of the battery, let's just call that 0 volts. If we call that 0, then this side must be 90 higher. That's 90. So we have 90 volts here on the same wire, and over here we have 0 volts. The potential difference across R1 is 90 volts. So V1 equals 90 volts. And the current in resistor R2, well, that should be easy. I2 is going to be V2 over R2, where the voltage drop across R2 is the same as it is in R1, 90 volts. So 90 volts over R2 is 30 ohms. It's going to give us a current of 3 amps. That easy. Equivalent resistance. Let's assume 3 identical lamps are connected in parallel with each other. If the resistance of each lamp is X ohms, what's the equivalent resistance of this parallel combination? Well, 1 over R equivalent is going to be 1 over X plus 1 over X plus 1 over X, which is equal to 3 over X. And if 1 over R equivalent is 3 over X, then R equivalent must be X over 3 ohms. Answer B. Let's take a look at a circuit that has 4 parallel resistors in it. The diagram below represents an electric circuit consisting of 4 resistors and a 12-volt battery. What is the current measured by ammeter A? What is the circuit's equivalent resistance? And how much power is dissipated in the 36 ohm resistor? A lot of questions, but again, if we make a VERP table, we'll probably answer all of them just in filling out that table. So let's call these R1, R2, R3, and R4. We'll make our table. We have elements R1, R2, R3, R4, and total V, I, R, and P. Fill in our lines here before we fill in what information we know right away from the circuit. And what do we know right away? R1 is 6 ohms, R2 is 12, R3 is 36, and R4 is 18. We also know our total voltage is 12. Well, you can also look at this battery. Remember, if we call this the 0 side, that means we have 0 volts here, 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 here. They're all connected together. And this is 12, 12, 12, 12. They're all on the same wire. So the voltage drop across each of these is 12 volts. 12, 12, 12, 12. We can now fill in our currents. I equals V over R. 12 over 6 is 2. 12 over 12, 1. 12 over 36, 1/3, 0.333. And 12 over 18, 2/3, 0.667. And the total current in a parallel circuit adds together Or we could have used the equivalent resistance formula to figure out what that's going to be. But if I add these currents together, 2 plus 1 plus 1/3 plus 2/3 is going to give me 4 amps. So R equals V over I, 12 over 4. We get 3 ohms there. Now let's stop for a second and check. We know the equivalent resistance of any parallel circuit has to be less than the smallest resistor in that configuration. So is 3 ohms less than all of our other resistors? It most certainly is. We probably did something right. Power, just V times I. Let's work our way right through here. 24, 12, 4, 12 times 2/3, 8, and add them all together, or 12 times 4, 48. So let's answer the questions it asked to begin with. What is the circuit's equivalent resistance? Req, right from our table, is 3 ohms. How much power? Well, what is the current measured by ammeter A? Well, A is measuring the current through R1, so let's say that I1 must be 2 amps. And finally, how much power is dissipated in the 36 ohm resistor? That's the power through resistor 3, which is going to be 4 watts, all right from our table. Looking at an ammeter in a parallel circuit again. In the circuit diagram shown below, ammeter A1 reads 10 amperes, so 10 amps right there. What's the reading of ammeter A2? Well, let's try a verb table solution again. If we call this R1, and this one's R2, then we have R1, R2 in total, and V, I, R, and P. We'll make our table. And start by filling in what we know. R1 is 20 ohms, R2 is 30 ohms. Our total current is 10 amps, because that's the combination current of what's going through our battery here. And as I look at this now, what's my next step going to be? Well, there's lots of different things I could do here. But what I'm going to do first, since we haven't done it this way yet, is I'm going to find the equivalent resistance of the circuit. So I'm going to say that our equivalent with only 2 resistors is going to be R1, R2. So what I would probably do first thing is draw an equivalent circuit where I'm going to put R2 and R3. I'm going to replace those by an equivalent resistor. So I would draw this circuit as we've got our 10 volts here. We've got R1, which is still 20 ohms. We've got our equivalent resistance between R2, 2 and 3. I'll write that as R23. I'll have to figure out what that is in a minute. And we've still got R4 down here, which is 20 ohms? Well, to find out R23, since it's in parallel, is going to be R2 times R3, 30 times 50 over 30 plus 50, which is 80. 150 over 80, or 1500 over 80, that's going to be about 18.75 ohms. That's a much easier circuit to analyze. Have current flowing in that direction. As we look at this, we'll go back to our verb table now. We have R1, R2, R3, and R4, and V, I, R, and P. All right. We'll get this started, and then we'll figure out what we know. R1 is 20 ohms. R2 is 30. R3 is 50. R4 is 20. Oops, and I forgot my row for total down here. Total. And our total voltage is going to be 10 volts. Okay, we know our total resistance because if these are all in series, 20 plus 18.75 plus 20 will give us our total. So 40 plus 18.75 gives us a total resistance of 58.75. That means our total current, I, must be V over R, which is going to be about 0.170 amps. If that's 0.170 amps, right there, let's think about it. On this version, that's 0.170 amps. It all goes through there. It's going to split here, but as it comes back through R4, we have the total current again, 0.170 amps. So we can fill in 0.170 here, and we can fill in 0.170 here. We'll figure out what else we can do right now. V equals IR, so the voltage drop across R1, 20 times 0.17, is going to be about 3.4. In R4, same math, 20 times 0.17, 3.4. Now, as I look at this, if we start here at 10 volts, I'm going to call that bottom side, the negative side, 0. That means this is 10, and across R1, we drop 3.4. So if we had 10, we dropped 3.4. That means we must have 6.6 over here. Down here at R4, if this is 0 side and it dropped 3.4, this side must be 3.4. So what's the potential difference across R2 and R3? Well, that's going to be 6.6 minus 3.4, which is 3.2. So R2 and R3 have the same voltage drop. Current flow now I can get from Ohm's law. I equals V over R. 3.2 over 30 is going to be 0.107. And 3.2 over 50 is going to be 0.064. And with the exception of a little bit of rounding error there, add these two together, we're going to get 0.17, which we should, because if we've got 0.17 coming this way, through R2 now we've got 0.107. That gets most of it. The remainder, 0.064, comes through here, and then they recombine again to give you 0.170. They add up. Now, to go finish this off, let's calculate our powers. V times I, 0.578, VI down here, 0.341 watts, 3.2 times 0.064, 0.205 watts, 3.4 times 0.17, 0.578 watts again, and our total 10 times 0.170 is just going to be 1.7 watts, which is what I should get when I add all these up, and I do. So that's how you could analyze a combination circuit. Simplify it until you can figure out some more of your unknowns and use your verb table to help organize all your thoughts. Well, so far we've been dealing with ideal voltage sources, batteries, and so on. But in reality, voltage sources typically have some amount of real internal resistance. Hopefully fairly small, but they have some amount of that. The terminal voltage of a voltage source is actually reduced slightly by the potential drop of current flowing through this internal resistance. So if we wanted to look at a real voltage source, we could model it as a source of EMF, electromotive force. That's not really a force, it's another term for potential, but what it really is that's the maximum voltage this could put out. And then you have this internal resistance. So your terminal voltage, VT, is what you actually measure across the terminals of the battery when you have some current flowing through here. Because you have current flowing, you're going to drop a little bit of your potential. Your EMF is going to be reduced a little bit by this internal resistance. So terminal voltage is going to be E minus I times your internal resistance. Let's take a look at a problem with two voltage sources here. Haven't done one of these yet. Find the current flowing through R3 if R3 has a value of 6 ohms. What's the power dissipated in R3? Well, to do this, the way I'm going to start is I'm going to set up my circuit and think for a minute. I'm going to call that point 0 volts because that's on the negative side of the battery, so that's going to be 12. And we'll say that we've got some current flowing. Let's call that I1 flowing through R1. Over here, we've got 0 volts on this side of the battery. They're connected by a wire, so they have to be the same. The positive side we'll call 16 volts, and we'll say that the current flowing this way through R2, let's call I2. That means if I1 is flowing this way and I2 is flowing this way, let's call this current 3. And it should be pretty easy to see by Kirchhoff's current law at this point that I3 is equal to I1 plus I2. All right, now that we've established that, let's see if we can't apply Kirchhoff's voltage law around some of these loops to get us some more information. If I apply Kirchhoff's voltage law around just this loop here, what that says is the sum of the potential drops around that loop must be equal to 0. So what I'm going to do is I'm going to list the positive and negative sides of each of these. This will be the positive side of the battery, the current of the resistor, the current is flowing and dropping potential this way, plus, minus, plus, minus, plus, minus. Now, as I make my loop around here, if I start down here, I always look at what sign I see first. If I'm going this way up, I see the negative sign of that battery first. So I'm going to write negative 12 volts plus, well, the next potential drop is going to be V equals IR, our current flow times our resistance by Ohm's law. So this will be 8 ohms times I1, so plus 8 I1. Then as I come around to this part of the loop, I've got I3 times R3. So that's going to be plus 6 I3. And at that point, I'm back to where I started. Must be equal to 0. I can do the same thing over here with this loop. Let's say we go this way around the loop to get us another equation. If I start down here, I see the negative side of this power supply first, so I could write minus 16 plus 12 I2 is what I come to next, plus 6 I3, and now I'm back to where I started, equals 0. So now I've got a system of equations with several different unknowns. Lots of different ways to solve them. Let's just work through this one in sort of the brute force method. Over here, let's start with this. Negative 12 plus 8 I1 plus 6 I3. Well, I3 is I1 plus I2, so that'll be 6 times I1 plus I2 equals 0. Or negative 12 plus 8 I1 plus 6 I1 plus 6 I2 equals 0. Or if I put that together, we could say that that's 14 I1, adding 8 and 6 I1, plus 6 I2 is going to be equal I1. I was able to get my first variable. Now what I can do is I can take that value and I can plug it back into one of my previous equations over here. What I'm going to do is take that and let's come over here and I'm going to start with this 14I1 plus 6I2 equals 12. But now 14I1 is 0.556 plus 6I2 equals 12. 14 times 0.556 is plus 6I2 equals 12. Fairly easy to solve that to say then that I2 is going to be equal to 0.703 amps. So I know I1, I know I2. I3 is just I1 plus I2. So I3 equals 0.556 plus I2, which is 0.703. I find that I3 is going to be equal to 1.26 amps. So find the current flowing through R3. That's I3. So we've done one of those. Let's make sure we box our answer so we don't lose it. Now, what's the power dissipated in R3? Well, for the power dissipated in R3, power 3, well, I know I and I know R. I can use power equals I squared R, where my I is 1.26 amps squared times the resistance of R3, 6 ohms, or 9.5 watts. So there's my other key answer. The current flowing through R3, 1.26 amps, and the power dissipated by R3, 9.5 watts. All right, let's do a problem with internal resistance now. We've got a 50 ohm and a 100 ohm resistor connected as shown to a battery with an EMF of 40 volts and an internal resistance of R. So there it is. Here, this entire thing is our battery. Find the value of R if the current in the circuit is 1 amp. What's the battery's terminal voltage? Well, over here I have two resistors in parallel. So the first thing I'm going to do is I'm going to redraw this as a nice series circuit where I'm replacing these by their equivalent resistance. So we'll have our 40 volts here. We still have our internal resistance, R, and our R equivalent between 150. Well, R equivalent is going to be 100 times 50 over 100 plus 50. So 100 times 50, 5,000 over 150. R equivalent is about 33.3 ohms. So I'll put that in here, 33.3 ohms. And our circuit just became a whole lot simpler. Now we know the current flowing through here is 1 amp. If that's the case, the current flowing through here is 1 amp as well. So as I run through and use Kirchhoff's voltage law around this loop, positive side, negative side of my battery, first thing I'm going to see is negative 40. Then I have 1 amp times R, so that's going to be plus 1R, or plus R, plus 33.3 times 1 amp, which is 33.3, must equal 0. So pretty easy to solve for this. R is going to be equal to 40 minus 33.3, or 6.7 ohms. We found the value of R. What's the battery's terminal voltage? Well, if we want the terminal voltage of our battery, V terminal is the battery's EMF minus IR. That's going to be our 40 volts minus I, 1 amp, times the internal resistance, 6.7 ohms. So 40 minus 6.7 is going to be 33.3 volts. Because our battery has some internal resistance, you don't get the whole 40 volts out when the circuit's in operation. You get 33.3 volts across the terminals of our battery. All right, let's take a look at a complex circuit with meters. Given the schematic diagram below, determine the reading of both the ammeter and the voltmeter. Well, what I'm going to do to start this off, we've got a couple power supplies here, is just look at this for a minute and see what we can figure out. We'll call this the 0 side of our battery, so that's 30 volts. That must be 30 volts here. We've got current flowing. We'll call this I1 flowing through R1. Over here we've got plus 5 volts. Well, I'm going to call this side 0 volts again because it's on the same wire. This must be 5 lower, so that must be negative 5 volts over there. If this is 0, we must have 0 volts over here as well. And we're trying to find the reading of both the ammeter and the voltmeter. All right, let's add I2 for the current flow through there, and we must have I1 flowing through here as well. That would be an I3. So let's see what we have as we apply Kirchhoff's voltage law around the loop. And what we're going to do is we're going to start here. As I apply Kirchhoff's voltage law, I'm going to see negative 30 first, plus 10 I1, plus 20 I1. Then I see the negative 5 before I get back to where I started, equals 0. Well, I've got one equation and one unknown. This just became relatively simple. What I can do then is a little bit of algebra here and say that I've got 30 I1 must equal 35. Therefore, I1 equals 35 over 30, or about 1.17 amps. I1 is what goes through the ammeter, so there's our first answer. All right, let's try and find the reading on the voltmeter. Well, the voltage drop across this R1 is going to be I1 times R1. So V1 equals I1 times R1. That drop then, I1 1.17 amps times R1, 10 ohms, is going to give us a drop of 11.7 volts. If this side is 30 and we drop 11.7, that must mean we have 18.3 volts left over here. And the voltmeter measures the difference from this point to that point. That's how it's attached. The difference between 18.3 and 0 volts is just 18.3 volts. So the voltmeter reads 18.3 volts. Our second answer. That wasn't nearly as bad as I expected when we first looked at it. All right, let's take a look at one more nice simple problem to round this out. 3 resistors, 4 ohms, 6 ohms, and 8 ohms, are connected in parallel in an electric circuit. The equivalent resistance of the circuit is, well, right away, if they're in parallel, I know that my equivalent resistance must be less than 4 ohms. Oh wait, there's our answer right there, less than 4 ohms. All of our other choices are larger than 4 ohms. Very little thinking required, just knowing that formula and a couple facts. Hopefully that gets you a great start with circuit analysis. Thanks so much for your time and watching educator.com. We'll talk to you again soon.